Do you want to cough before we start?
Go for it.
Welcome to the Hackaday podcast. My name is Mike Szczys. I'm editor-in-chief of Hackaday.
Hey, I'm Elliot Williams. I'm also editor-in-chief of Hackaday.
This is episode 148. Today we're talking about Pokemon trades, anniversary iPod prototype, stupid satellite tricks, and LED strip sensors.
Well, starting off the news this week, we have something actually fairly sad, and that is that Sanjay Mortimer, a pioneer in 3D printing and founder of the E3D company, died a few weeks ago, and it just came to light about a week and a half ago. Joshua Vasquez wrote a marvelous piece about him, remembering Sanjay Mortimer, pioneer and visionary in 3D printing. I know him from way back in the RepRap days when he was just starting up this company, E3D. And one of the things they had really founded the company on was a new hot-end design. And at this point in time, 3D printer people hadn't really figured out what parts of the hot end need to be hot and what parts need to be cold and how to make the heat breaks work. And everybody was just kind of putting that together. If you're pushing plastic through and melting it, the unmelted part needs to be like a piston to push the melted part out the end. And this aspect of 3D printing was just being figured out, and Sanjay was on the cutting edge of it. And it's absolutely no exaggeration to say that almost every printer out there has a derivative of his hot-end design. And, you know, whether it's a Chinese knockoff of it or whether it's the real deal E3D versions. And, of course, they've improved on everything since then, and innovation moves forward. E3D's been at the front of this mostly because of Sanjay. And Joshua has a really nice reminiscence of his collaboration with Sanjay and working on Josh's tool changer module and Sanjay taking an interest in it, and the two of them then kind of collaborating together and inspiring each other mutually. And I think that's really the story that everybody tells about Sanjay who knew him directly. Like if you look around the 3D printing / RepRap community, everyone who knows him says that he's been super enthusiastic, and what can you say? He was just a 3D printing fanatic like the rest of us, and that means he loves it and the passion comes out. And that makes his way too young passing a bit of a sad moment.
This is a journey into sound.
What's that sound?
What's that sound?
All right, and then it's time for What's That Sound? Mike, did you enjoy that one last week?
I did. It was so nice of you to pick Minecraft sounds for me.
Oh, you guessed it.
Guessed it. There's no guessing, buddy.
Yeah, right?
I knew it right away. I can't believe we had so few responses.
What, we got 23 correct answers here? That's not super few.
It should be 123.
You expected it to be 1,023,000.
Yeah, exactly.
Yeah, fair enough.
I think if you had a reply button on your podcast app, then we would have had thousands. You know, I'm usually like literally washing the bathroom, washing the dishes, driving a car.
Exactly.
You know, my hands are occupied when I'm listening to podcasts usually.
I've actually just started playing with my son, of all things, about a month and a bit ago. So I'm actually a
fun.
Minecraft noob, and it's been super fun. And those sounds are definitely etched in my brain, though.
Yeah, I think the harder thing would have been to just do the ambient zombie sounds. Because you started this one out with the the pre-brains sound. But you know, there's a bunch of those. Like when you're down in the depths digging and you don't have like direct line of sight to the zombies, they make like different sounds to kind of like warn you.
Hear them around the corner. Yeah, totally.
How are we going to draw this week?
Many, many shows ago, I wrote a neat little random utility that I guess isn't totally random. It's just unpredictable before you run it. It takes a file, or back then I used input from a video camera, hashes it, and then takes the last few digits off that and uses that to create the random number. And so that's what I'm going to use this time, except I think instead of running the video camera, I'm just going to run it on the image that is the Hackaday podcast logo, just for fun. And the idea here is that I have no idea what it's going to be ahead of time. You have no idea what it's going to be ahead of time. But if you had this picture and you had my code, you could run it and verify that I drew the right random number. I'll have to include them all in the show notes. Let's see. Here we go. Here, random hash. How many people? 23 people. And logo Mike square big JPEG. And the magic number is 6. Congratulations to Jort. Minecraft mob noises, spider, zombie, skeleton, creeper, and finally a cow. Ooh, I don't remember a spider in there. You still win. We're not taking off points.
We're not. We're going to send you a shirt with 1 fewer sleeves because you put spider in there.
Fantastic. Best absurd nickname of the week this week, I think, has to go to Toby Larone because they're yummy. And probably a second place goes to Lord of the Things. Congratulations.
Lord of the Things. That's a great alias, I got to say. I like that one.
I've had compression algorithms on the brain for a couple weeks now. And this week's first hack, cracking the Spotify code, really tickled my fancy because of that. Peter Boone has looked into the little variable length barcode thing that Spotify uses to encode playlists. And this is a really great, very detailed dive into how they tell which playlist you're talking about based on this set of, I guess it's 23 stripes of 8 possible different lengths each. And that makes you start thinking that you understand it already. But trust me, it is more complicated than you think it is. Before I get into the cool algorithms here, I'm a little bit of a Spotify noob. Do you even know what these are used for, Mike?
I don't. I've used Spotify and I somehow, I don't currently use it. It's been a while. I somehow missed these codes, but I believe that they're there. And I'm a sucker for barcodes. Like, I love barcode technology. And this one's especially interesting because it is so dependent on a very small difference in the height of these bars.
Which you would think is really hard to decode, and you'd be right. But these almost have more in common with QR codes than they do with regular barcodes, in that there's a ton of redundancy built into it. And so exactly that situation that you're worried about, Mike, that, you know, one of them is a tiny bit taller or shorter than the other, is something that they're robust to. And that's because of what I'm about to explain to you, the crazy encryption method. So it starts off with, instead of like a URL or something, all of the playlists get a 30-bit media reference number. And then onto these, an 8-bit CRC is added. So you can tell if you've got that number right or not. And here's where it gets interesting. On top of that, they add in a convolutional encoding and decoding. And basically what that means is you take another short number and you kind of slide it along the long binary number. And they actually do this convolution with 2 different kernels. So they do it with 2 different complementary binary patterns. So they take an input 45 bits. By convoluting it once with this number and then convoluting it once with that number, they actually get 90 bits out of that. And so you're thinking, what is the point here? They're taking a 37-bit number and they're embedding it in this much bigger space. And the idea is that if there are any little errors in any of those bits in this bigger space, it'll still look like it's closest to the right number. And so you get this kind of robustness to errors here. And then they turn it up to 11. Because they've got so much redundance, a factor of 2, they can afford to drop a bunch of the bits. And they actually drop every 3rd bit out of this sequence. So from 45, they convolute it out to 90 bits, and then they shrink it back down to 60 bits. Then they take these 60 bits and they shuffle them all up. They permute them so that none of the previously adjacent bits are adjacent to each other. And what that does is that means that an error is spread out effectively across the different bars. And then, to top it off, they make the bar height, of which there are 8, refer to, that's 3 binary bits, right? And they encode those using a gray code. So the difference one height to the next is always 1 bit, and not like if you did it in binary where it switches from, say, 3, which is 0, 1, 1, to 4, which is 1, 0, 0. That's 3 bits all flipping, and that could really mess your algorithm up. They gray code it instead so that only 1 bit is different. Anyway, the long and the short of this is that this crazy encoding mechanism ends up with a 37-bit number encoded in 23 of these stripes that have 8 possible different lengths. But they can be wrong by a whole bunch, and it'll still come up with the right number and then give you the right playlist. If this sounds like insane technology to put on a barcode, I think it actually is. This kind of convolutional encoding and you may have heard of the Viterbi algorithm, which is a quick way to undo convolutional encoding. It's a quick way to figure out what the closest neighbor is to the signal you receive back. Has been used on like spaceships since I think Voyager 1. And all of the deep space probes use it because it helps get messages that are interrupted back to Earth safely. And this is the technology they're using in these funny barcodes? What?
I think that makes sense. I mean, in like when you come along with good ideas, you might as well just apply them to the next thing that you need.
That's totally true. And what surprised me is how old this stuff was in a way. I mean, the Viterbi stuff comes back from the 60s, I think, and was, like I said, implemented on Voyager. So that's from the 70s. So actually, by now, this is totally old hat. I'm sure it's taught in everybody's, second year, third year college signals engineering class or something. I didn't learn it in college. Anyway, it's really interesting and a great deep dive into this topic by Peter Boone here. If you want to check out other crazy barcodes where the length matters and you live in the States, you've probably actually seen them on envelopes on the outside in the form of the USPS Intelligent Mail barcode. This Spotify code reminded me of that a little bit, and so I'll throw in the reference to Intelligent Mail for you to check that out at your leisure.
It does remind of that, but I think it's a little more brilliant. If you look at those on the US Mail, there's only 2 bar sizes, right? There's like a full bar and a half bar.
There's 4. There's a wide bar, a thin bar, and then an up bar and a down bar. And so they're encoding 2 bits with each symbol.
Yeah, so the thing that I like about this one, branding wise, it's really smart because it uses the Spotify logo to indicate the largest width of bar.
Exactly.
And so like instead of just being some random barcode, it's actually got the company's logo in it. So it's, smart for them. And that is like crucial, right? You need that so you know what the 7 length bar is. But if you look at it, they vertically align to center for these. And so what you actually have is 2 copies of the sizes of bars. If you just split the whole thing in half.
The upper side and the lower side.
Right.
Yeah.
And so if you have a smudge or a bad image or something, you could technically correct for that.
Oh, there's some redundancy there that I didn't even think of.
Yeah, so I thought that was interesting. I'm not sure they're using that, but you could use that if you wanted to because they should be exactly the same on the top half as on the bottom half.
That's brilliant. If they're doing all the rest of this error correction, they have to be doing that.
I think it's just built into the smartphone app, right? Like it uses your smartphone camera and there's just a reader for these.
Right. The other thing you could do, since these have so much redundancy built into them, is you could probably tweak the shapes a little bit and kind of draw something cool. Like, how you could do that with QR codes, right? Because there's enough redundancy in the encoding that you can like put a picture of yourself in the middle of the QR code. And as long as there are enough good bits in there, it'll decode just fine. You could probably do that with this. You could like make cool wavy patterns or something.
There was a great article this week that Ryan Flowers wrote about a look at one of the late prototypes for the original iPod. And I think that it comes as no surprise, or maybe a little surprise, that it's 20 years since the iPod first came out. And I can't believe that we haven't seen this before. Maybe we have. I certainly haven't. It is like, do you know where this case technology comes from, Elliot? Are these resin prototypes?
Yeah, I don't know. It's all like yellow and faded in this one. Right. You actually have to look at it. It's the least iDevice looking thing because it looks like it's an old Apple computer or something. It's so yellowed. But yeah, I have no idea what the plastic technology is.
Well, I've seen this material before for prototyping cases, and I think it comes down to that idea that if you're going to show your engineering prototype to someone for their approval, the people holding the purse strings, it's gotta like at least look nice and finished, like you know what you're doing. And I guess it doesn't really matter what's going on the inside, but if you're going to hand it to someone to be like, try this out. And so what it has on it is the little iPod screen. The iPod screen back then is like if you make a circle with your thumb and your forefinger, it's like that size. That's maybe like 1/20th the footprint of the front of the case of this thing.
Yeah, right.
There's then a big wheel, like knob, like a giant volume knob from 70s hi-fi equipment with a button in the middle of it sticking up. And then these 4 black square buttons below it that say up, down, left, right with a label maker label on them. And then the next best thing for me is off to one side, there's a big 20-pin shrouded header and a hunk of PCB sticking out of it. And I love that part of it.
Right.
So this actually has a very late stage iPod guts in it. And if you turn it over, there's not much to it. I mean, there is the actual scrolling mechanism that goes through the front of the case. And there is what I assume is one of those mini hard drives that they actually had in these. And coming off the top, there's a connector. But then you get to see the flexible PCBs that made kind of the ability to fit this into the small case possible. And it's mostly an empty husk. But it makes me think back to a time when you probably didn't just have a 3D printer, on the desk of your home workshop, much less your work workshop. And so getting one of these cases built would have been costly. And so they probably ran off a whole bunch of them. And then as they miniaturized the design, it took up less and less space, but they didn't make a new case for it.
Could be. The thing that was the calling card of the original iPod was this jog dial wheel, right? And it was capacitive sense. And that's missing here. And in its place is kind of like it gives you the idea of the interaction that they want, but it's nowhere near as slick. It's obviously like a turny wheel with a big sticky uppy button in the middle.
So that's interesting because my recollection is that the original iPod didn't have the click wheel as we remember it. It actually had a physical jog wheel, and then it had a ring of buttons around the outside.
Man, I never had one of the first generations. I've definitely...
I might be wrong.
I
I know for certain there was a ring of physical buttons around the outside of the jog wheel.
Yeah, absolutely.
And then whether or not it was a physically turn or if it was the capacitive touch turn, I'm not certain on that.
Maybe the cap touch one just came out later.
Yeah, because later, remember, they got rid of that buttons. Like I think it was the very next generation. And again, I'm sorry, everyone that loves the Apple system. I have not... the only iPod I've ever owned, I bought broken on eBay and then fixed and put a compact flash card on it and put Rockbox. So it's like totally not the Apple experience. I think it was called Rockbox. I'm not sure what it's called. So I'm sorry. I'm sure I'm slaughtering this. But yeah, when they moved to that new generation, that was the future. Like that capacitive wheel. And then the wheel itself had the clicks in it kind of like the touchpads on laptops do now. But I'm not sure that touchpads on laptops clicked back then. We're talking 2001.
Yeah, exactly. I don't think so.
Yeah, I think you had like 2 buttons below the touchpad.
Yeah, exactly.
So, it's crazy to think about where we've come with user input. And I still think we're like Luddites. I mean, really, can you believe that we take our greasy fingers and touch the beautiful high-density screens that we're supposed to be looking at with our greasy fingerprints? Like, who does that? Like, seriously, I need to go join a cell phone company, Elliot, because I think the entire back plate of your phone should be a touch interface. And you should scroll on the back of the phone with like a cursor or something.
Yeah, but then what do you hold the phone with?
Well, come on, details, man. Go with the vision.
We'll work it out in software.
Yeah.
My next hack is one of the main sources of hacker tears out there. Supercapacitors versus batteries again. A new video by Andreas Szczys. Supercaps are up there with Peltier coolers in my mind as things that sound really cool and then when you go to implement them, all of the details come crushing down on you. And Andreas makes a great survey of all of the problems with supercapacitors and why they're maybe not so super in this video. The main problem is that when you have a battery, it kind of holds on to its voltage until it gets near the end of its life, and then it just kind of falls precipitously off the edge. Whereas supercapacitors, like capacitors, I mean, they're just capacitors, drop the voltage essentially linearly as they discharge across their life. And this means if you charge up your supercap to 5 volts and then your circuit cuts out at 2.5 volts, you can really only use half of the thing's capacity. Andreas suggests the way around this is to put a boost converter on the other side of it. So you run your supercap all the way out, but you use a boost converter to keep the voltage on the output side stable. And that does make sense, but it's more complicated.
It is interesting because I think about supercapacitors as having kind of a different role. You know, the thing that everybody wants about them, at least that I want about them, is they charge up so quickly compared to batteries.
Yeah.
And then there's repeatability. You know, the thing about repeatability is I know that these big electrolytic capacitors go bad over time, but it's on the span of years, so it's probably fine. But
they kind of go bad. And that was more of a like early 2000s thing. That was some bad batches that came out.
Really?
Yeah, I mean, electrolytics do go bad over time, but like a decade time.
The side effect, though, is they're so good at charging up very, very quickly, but they're also very good at discharging very, very quickly.
Exactly.
And he makes the point in the video that, like, that's not really what we're looking for. You know, like, generally, we want to have, like, consistent, stable voltage and you know, a reasonable amount of current draw. Whereas, were you at that SuperCon where Crux brought his platter launcher?
Yeah.
Yeah. So like he's putting hard drive platters on top of a coil of wire and then using a supercapacitor bank to discharge everything into the coil, creating a magnetic field that launches the platters into the air like, I don't know, 10 meters. So, so like that works out really well. And then the other thing that Andreas talks about is the fast charge, fast discharge of like regenerative braking. And I hadn't really thought about it before, but that's brilliant. That's exactly what you need to use those for.
Yeah, and so that's, I guess, his point is that there are places where supercaps make sense, and you got it. Anything where you're going to have a lot of repeated cycles, like charge-discharge on regenerative braking, and you don't need to store it for very long. The other great application, I think, is solar, because you kind of need the boost and buck power converters anyway. Like coming in from the solar cell, you need a buck converter and or a PowerPoint tracker. And then leaving whatever your supercapacitor is, you just put another boost on that. So great for solar. They do well when it's freezing, he mentions, which is one I didn't know. And their killer application is what Mike pointed out, that they can deliver high current pulses if you need them to. And so supercaps have, in that sense, kind of a low energy density. They're heavy for how much energy they contain, but they can have a high power density. That is, they can really put out the juice, maximum power outflow for their weight. And that's kind of cool. This kind of problem with capacitors, that they want to give you a lot of current in the beginning, is also what's behind the two capacitor paradox. And if you're thinking of doing anything where you charge up caps and use them for energy storage, you should know this one. And it goes like this. You take two capacitors, one of them's charged, one of them's uncharged, and you connect them together. What happens? The answer is, at the end, they have to have taken the charge that was all on the first one and split it up evenly between the two capacitors. So they'll both be at the same voltage. The problem is that the energy stored in a capacitor is proportional to the voltage squared. And so you have the voltage on one and you have the voltage on the other, which means you've quartered the energy in either of them, which means you've halved the total energy just by connecting them together. And that's the paradox, right? Is that energy shouldn't be created or destroyed. And you've just taken two capacitors, hooked them up, and the resulting system has half that energy in the end. Where did it go? And the answer to the capacitor paradox is wire resistance and internal heating in the real world. And actually, I've done this experiment a few times, and you end up with not half the voltage on either of them. You end up with a little bit even less than half the voltage on the two capacitors. And that's because you aren't using perfectly conducting wires. Because you have real-world wires, when you plug the charged one up to the uncharged one, it wants to pass essentially an infinite current from the one side to the other because the voltage, you're dividing by 0 because you've got no voltage on that other one. And so it shoves a lot of current through in the beginning. And if you have any finite resistance in that wire, that consumes a lot of the energy in the resistive loss, the I squared R loss. And once I say squared there, those of you doing math should be like, yeah, that probably checks out. Anyway, the take-home point of this is that if you want to charge up capacitors, to avoid this two capacitor paradox and avoid throwing away all of your power into heating up wires, what you want to do is charge them with constant current rather than constant voltage. So if you end up doing any projects with supercapacitors, this is the other thing to remember that Andreas actually didn't mention in his video, is that you're going to need a boost converter and you're also going to need a constant current charger, not a constant voltage charger.
We are on to an amazing tip that comes out of Mike Harrison of Mike's Electric Stuff video. This is putting a 2-wire sensor onto LED strips without adding. So you're actually using the strip itself. It's pretty interesting. The strips are not addressable like you might be thinking of. They're just single color LED strips that run at 24 volts. So they have a voltage rail and they have a ground rail. But when you start to look at these, they actually gang up about 6 of these LEDs at once and then run a resistor through them to set the current for them. The voltage drop over each LED on these strips is something like 3 volts. So it means that if you want to get them to light up, you have to get the voltage above 18 volts. Otherwise, current's not going to flow. And so if you keep it below that 18 volts, the lights aren't going to light up. You can actually add some extra circuitry to the strip. For instance, he's using a 15-volt Zener diode on the low side. And then he is tapping in upstream of the 6 LED arrays and downstream of the 6 LED arrays and adding a transistor that's driven by a microcontroller. Now, there's a whole bunch of other stuff in there, like a 3.3-volt regulator, and then like the actual sensor itself. It might be an accelerometer or a temperature sensor or whatnot. But the point is that this microcontroller can decide whether or not current is flowing through this like side channel that's going around the 6 LEDs. And if it is, it allows just a trickle of something like 9 volts of power to go through the strip, therefore not lighting up the LEDs. But by turning that on and off, you can actually send pulses, and then those pulse widths can be your data channel. So whatever your accelerometer is doing, you can send like some, I guess, binary value through there. If you're doing temperature, you could send like an analog value based on like the duty cycle that's happening here. And the only issue is this only works when the pulse width modulation control of the LEDs is off. And so that's something he was also putting downstream. But if it is PWM, it's off a portion of the time anyway. So as long as you don't run it at 100%, there's always going to be some off time, and then you can have circuitry on the other end that catches these lower voltage pulses that are actually encoding data.
This is just totally one of those classic Mike Harrison hacks, right? He's got a very weird niche requirement. He's got a super long LED strip and he needs a sensor out at the other end, and he doesn't want to add extra wiring to it. And so how are you going to get data back across this power line, essentially? How are you going to power the sensor at the other end and get its data back? And this trick with the Zener diodes is absolutely brilliant because it, like you said, it lets you run the microcontroller, and then when the microcontroller passes more current through it, it can send signals back to the power supply doing the PWM on the front side. Kudos. He must just have so much fun thinking up these crazy solutions.
Yeah, and I kind of wonder where this one came from because it's an outdoor installation, I believe. And so you have the outdoor rated LED strips, and you don't want to be like, how do I run a signal wire along, and make sure that it's like outdoor rated, that's just going to be like a whole can of worms. So I just wonder if he did it at the end of the design process, or is like, oh, we should add this thing in. Or if it was like at the beginning. I suppose it doesn't matter. I'm just kind of curious about that. But in this case, you just have to tap into the wire at the low side end of the strip, which you're going to do anyway because you have the pulse width modulation control there. Yeah. And then wherever you're going to put your 2-wire sensor along the strip, you just have to make sure that you tap in and then make that waterproof.
It's not even particularly more solder connections. You have the PWM board at the front and the sensor board at the end. You kind of had to have those one way or the other.
I'm sure my explanation doesn't do it as much justice as it should. He's got about like a 9-minute video, and I think, maybe half of that is spent hand drawing a schematic and working through it. And I think it's really apparent what's going on there. But one thing's for sure, you want to write down the link to this one because, a few years from now, you're going to find a use for it, and you're going to have to come back and try to find it again.
All right, my last hack of the week is bridging game worlds with the impossible Pokemon trade. This is a cute little project by Gautier to take Pokemon out of the Generation 2 world and into the Generation 3 world. And I'm not a Pokemon addict, I'll admit it, but basically the lay of the land is like this. There are 4 generations of Pokemon games, and Generations 1 and 2 had a cable that you could connect between players and you could trade Pokemons with each other. And Generations 3 and 4 have these same cables. There's no way to get from Generation 2 to Generation 3. So if you have some Pokemon stuck way back on Generation 1 and you want to play with them on Generation 4, they can't cross that barrier. Of course, there have been some save file hacks and things like this, people binary reverse engineering it. But that's not the same as taking 2 consoles, plugging them together with a wire in between them, and like physically typing OK on either one. And so that's the experience that Gautier is going for here. To do it, he makes a man-in-the-middle microcontroller board that understands both the Gen 2 protocol and the Gen 3 protocol, translates between them on the fly, makes sure that all the data that goes in one way and the other way to make the trade happen takes place, and does some really clever stats conversion along the way to make sure that your Pokemon plays the same in the new world where they had totally different statistics than in the old world. And the whole thing is a great look into how Pokemon was coded on the inside, and then what signals go over the wire when you cut the Pokemon cable in half and hook up a logic analyzer to it.
So first of all, what kind of memory do these cartridges have in them? Is it like battery-backed RAM? Because they said when the battery dies, it's just gone. The saves are gone.
We actually had a hack a few weeks ago on that where someone put FRAM into one of these Pokemon cards so that it would never again lose its memory.
Yeah, so that's just wild. Just because I've always used microcontrollers that had EEPROM built into them. And so it would, like 10,000 rewrites, I think those are rated for, like on the AVR ones.
Yeah.
So it would seem like it would be okay with these cartridges, but they're built in such a different era, and buying parts at scale, it just seems like putting a battery in every cartridge is expensive and difficult too. So I was surprised by that. But the other thing is, and bear with me here, Elliot. So this is a great story, and I loved watching this video and going through it. But I've been reading a lot about legacy government computer systems, and I think. There's a bunch of different ones, but I think it was probably like unemployment systems. Mm-hmm. And so when they were first computerized, they were, written in COBOL or whatever. It's like mainframe programs, right? And then I don't remember what state it was, but they finally did like a web program that people can go and apply through instead of using like the phone system or like doing it in person or whatever. But the 2 systems were never connected up. So the mainframe system still runs everything. Mm-hmm. And the web system just submits it. And so workers then have to take what you submitted on the web system and manually enter it into the mainframe system. And so there's all kinds of errors, and it takes a really long time, and the system is just basically broken. This is the person that they need to hire.
Right?
This is the exact problem that they're having, is like, how do you get it from Pokemon 2 to Pokemon 3? Yep. And these people are doing a great job of figuring it out. And I know it's totally not as fun to do that for some, like green text on black screen, COBOL thing. But at the same time, it kind of is, because I think a lot of people would like scratch their brain and they'd want to solve that problem. I just wish there was an easy system that we could get to find people who are doing this kind of work and get them to do like serious infrastructure work that would move things forward for a lot of people.
Like I said, I never played Pokemon. So to me, this seems like a frivolous use of the technology. And you're suggesting it could be used for even greater good. But, think about it. He's able to trade a red Gyarados into Generation 3 and have the stats check out. A red Gyarados. Anyway, it's a great video. I actually expected it to be more about the hardware, since it's basically a hardware hack. Except the hardware doesn't even enter the video until minute 13. And that's just to show you briefly the PCB. And all you can really glean from it is that the circuit board has a microcontroller on it, a voltage regulator, and then the 2 plugs to plug into. I think all the rest is done in code, and thus the code/signal centricness of the video totally makes sense. It's a really cool look into the way they did some pretty sophisticated interactions between two different consoles way back in the day.
Yeah, I mean, I noticed on that board that they've got a Tag Connect footprint for programming on the board. So I'm guessing the day job is hardware, but it's really cool to see this stuff done, at home on the workbench. Well, let's talk about some interesting radio research that's being done around the red planet, Elliot. The ESA wrote a really interesting article about taking measurements about the atmosphere of Mars by sending radio signals through them and then analyzing what you get out the other side. And I had no idea that this was a thing, and it turns out that they actually do it around Earth as well. So if you have a sender and a receiver, and you send a known signal that's not it doesn't have a lot of changes of data, and it's some very vanilla, open mic type of signal, and you send it through clear vacuum and record what you get, and then you send it through a portion of the atmosphere and record what you get, and then compare the two readings, you can actually tell a lot about the molecules of not vacuum that signal went through. And they've been doing this with the Mars atmosphere because there are satellites around it. But the thing is, they've been sending signals back to Earth and measuring them. And then they've been waiting until the Earth and the satellite have a little bit of Mars atmosphere between them. And then they've been sending it back to Earth and then analyzing them. And the problem is that opportunity doesn't arise all that often. Orbital mechanics of where the satellite is around Mars and where Earth is in relation to the two of those makes it difficult. The ESA has figured out how to do it between two of their satellites that are currently in orbit around Mars, and it will allow them in about a 2 months' time to take as many measurements as they would have in 18 years.
Oh my God. I always think that a lot of space science is just kind of doing the most you can with what you've got, because it's hella expensive to get satellites out around Mars. And so, you might have put the satellite out there for one thing, and then you're like, well, we've got the satellite there. We might as well use it for something. And then they're sitting around scratching their heads going, what the hell can we measure with this? What if we shoot through the atmosphere? Yeah, let's do that.
Well, and it totally becomes hackers at the European Space Agency too, because the two satellites that they're using for this were never meant to be used for this. They're satellites that are meant to relay from ground hardware on Mars up to the satellite and then send it back to Earth. And so they didn't actually have the systems in place to talk to each other, except software-defined radio. So they actually went to the radio manufacturer and they're like, look, we tried this out with what's on there. It's not really ideal for this. They were able to make a communication, but they weren't able to do it with this specially crafted signal that they needed to get good readings. Mm-hmm. And so they went to that company. They're like, hey, can you put in, quote, an empty patch? And they did. And they pushed the software update. It changed the way that the radio functions. And, when these satellites are not being used for their slated ground mission, they're going to be doing these readings.
My first quick hack this week is not particularly techy, but it's really cool. Kerchu22 has assistive tech and video games. It's a joystick that you can steer by leaning your head to the side, and it's basically a simple cardboard bumper ring around the head. You nod forward or you tilt your head to the side, and it presses two contacts together to click. But you can use it like a joystick, except with your head in the middle. Potentially totally useful for quadriplegics to get the signal out. Next up, my major is gaming. This is a series of classes from a college course in programming video games from Memorial University by Dave Churchill. It's a fantastic series walking you through how to make 2D video games with no fancy libraries whatsoever. And finally, Afro Rack. Get down to some African tunes with this homebrew synth. Get it? Euro Rack, Afro Rack. It's marvelous. Brian has made this fantastically convoluted Eurorack synthesizer system and then added to it physical shakers and drums and things like this that he made himself from hand-wound solenoids that have quite a bit of oomph to them. It's a really nice rig he's built himself up there. It's got a lot of components that are actually in my synthesizer rack, including he has a great video on Renee Schmitz's MS-20 filter, which is absolutely a filter you should make. I have 2 of them in my rack.
First up on my list, secret ingredient for 3D printed circuit traces, electroplating. Donald Papp picked up on this one, which is a project from HoboChild. I've always kind of been wondering what conductive filament's real purpose is, and this is it. Go check this out. So you print your traces with the conductive filament, and they won't work very well. I mean, Donald Papp points out that these are like printing resistors rather than printing wires. But they do conduct well enough that you can then use them for electroplating, which is totally possible to do in your home lab. So there's a lot of potential here, and if you have a 3D printer and want to put circuitry into that, check it out. Next up, touchscreen-powered USB hub selectively powers down devices. Robin Keary wrote this one on a hack that Matt G pulled off. If you think about USB hubs, it's a great way to power a bunch of devices, and most hubs have at least one toggle switch that'll shut off the entire hub. If you're lucky, you might have a toggle switch per port, but you're still just looking at like black USB cables plugged into each port. Which device are you trying to turn off? This actually takes a tablet, turns it into a touchscreen interface that'll let you know exactly which port you're turning off because you can label it with the device that it controls. And finally, the safest model roller coaster. Brian McAvoy wrote this one about a video that Jared Holliday made. It is the most over-engineered scale model of a roller coaster that you've ever seen, and that is because it's trying to simulate the real thing. It even uses the control hardware that you would find on the actual human-rideable installations of these, and it's a great way to step up the engineering skills that you might one day use when someone comes and asks you to build a roller coaster.
Happens to me every day.
Hey, it doesn't happen until it does.
True that. And when it does, if you're like, I don't know anything about designing roller coasters, then you're out of the game, aren't you?
It's time for our can't miss articles of the week. This is long form content written by excellent Hackaday writers. Elliot, what article did you pick this week?
My choice this week was Jenny List's roundup of news from space, spacing out telescopes, politics, and spacecraft design. And I picked it because there are a couple stories in here that are super interesting to hackers, I think. But let's start off with some news first, and that's about the James Webb Telescope. They had this a near-death experience. The quote is that it was an unplanned release of a clamp band, and it sent a jolt through the telescope, and they've tested it out, and it's okay. But unplanned release of whatever is... A sudden unplanned release is like NASA code for an almost horrible disaster. Like when they have test airplanes blow up, or they're like, it was a sudden unplanned disassembly, So anything like that sounds like a clamp band failed on them.
Yeah, it's like when you're carrying the pile of dishes over to the sink and a glass falls off and you just catch it before it hits the floor. That's like what I have in my mind is like, ooh, this must have been a close one.
Except it's a multi-billion-dollar stack of dishes, right?
Yes.
With incredibly delicate scientific instruments on board. Yeah, but good news, they say it checks out just fine. So, that was a tight one.
Close one.
There's been continuing kerfuffle in the hole in the International Space Station incident. There was a hole, it really looks from the images that I've seen of it like it was on purpose drilled in one of the Soyuz capsules in the space station. They fixed it up with some epoxy, but having what looks like sabotage or a horrible mistake is kind of disconcerting. And at this point, the Russians are blaming it on an American. How she snuck in there to drill inside the Russian side of things is anyone's guess, but there's been bad blood between the States and Russia about the ISS for a while now, and it seems like it's getting worse. But then to some good news, and that is NASA put out its report on the state of the art in small satellites 2021. The last time NASA took a look at small satellites was way back in 2013, and it was kind of the early beginnings of the small satellites / nano satellites / CubeSats revolution. What was really neat about reading this report is that it gives you an idea of just how much of a difference having affordable space launch has made things. Back in 2013, 60% of satellites launched were over 600 kilograms. Now, 94% of satellites launched are under 600 kilograms. Nobody is launching these giant satellites anymore. They're all smaller. And that includes the kind of microsatellite, nanosatellite, and picosatellite, the kind of tens of kilograms satellites that a lot of the CubeSats fall into. And so there's some really neat insight here. If you're at all into kind of armchair space or amateur space, or you're just interested in the state of the art of, I don't know what, solar cells it gets into. There's a really marvelous chart on how to assess technology for space, and that's based on these technology maturity assessment. And it starts off with, has an identical unit been successfully operated in identical configuration? And then it's like, has an identical unit in a different configuration been launched? And that's a slightly less confidence. And it's like, has a prototype similar enough been successfully operated in space? And then it's like, has a prototype been operated in a similar environment but not in space? And then it's like, has a breadboard unit been demonstrated in a relevant environment? And it goes down this list to, has a breadboard been demonstrated in a lab environment? Has there been a proof of concept? Has a concept for the application even been formulated? That's tech readiness level 2. Versus tech readiness level 1, have basic principles been observed and reported? And if you answer no to that one, there's a big bar at the bottom in all caps that says, rethink position regarding this technology, ! Don't send that stuff to space, son. Anyway, it's a marvelous document, and it points out how much more science has been done on smaller satellites these days. And there even are some CubeSats that look like they're going to get into further out orbits. So they're going to kind of leave the low Earth orbits where most CubeSats are. They've got enough propulsion on them to go out into some of those other funny orbits much further out. So really interesting work being done in small satellites these days, and it's all summed up for you here. And if you're interested in armchair space, you should go check it out.
I thought Joshua Vasquez wrote a wonderful article this week called Made to Spec, The Coming Age of Prototyping as a Service. And in it, he goes through his thoughts on his time developing prototypes and products where, he would be stuck in a machine shop, like making every single part along the way. And the thing is, over time, services have risen up that allow you to actually go in, put in your CAD files, and they will fab the part and send it to you. And this can be done in a number of different materials. I think people are already familiar with, available to order 3D printing. Obviously, there's also sheet good cutting, so you can get things that are cut out of acrylic or cut out of plywood. But now we're getting to the point where CNC parts made out of metal are also able to be ordered through these services. And he has a whole discussion on the ins and outs of what that is going to mean.
I think this is going to be a game changer in the long run, because while you're prototyping something, and Josh kind of hints at this in the closing of this article, while you're prototyping something, you might enjoy doing it yourself in the shop, and you might miss it if you ship that out. But you also lose the ability to have it easily replicated by other people. This makes this kind of high-tech materials available to the home gamer who doesn't have their own CNC machine and doesn't want to hassle with cutting out carbon fiber, or water jetting metal, or injection molding things. There's all this stuff that you don't want to do at home, but the people who are following your project also don't want to do at home. It doesn't just enable you, the prototyper, to get it done. It enables other people who are following along and maybe want to build your project to say, make it so.
I think also people that are doing serious work, like, you don't want to spend all your time cutting things out of steel if you don't have to. Like, time is money on that. And if you have these services that are going to do it for you, that is a viable option. Some of the downsides, though, that Joshua talks about is you're far away from the material now, right? And so, like, you just know, you know a lot more about what designs are going to work and, like, the things, the gotchas that are going to pop up if you're the one that is wasting the time when something doesn't work, rather than wasting some money and some waiting time for someone to send you a part that you find out doesn't work. There's that. I think on the other hand, there's just so many processes that we can't be experts on. He talks about a service in here that will do like low run injection molding, which I had no idea that happened. They're doing, I think, the 3D printed resin molds for injection molding rather than, milled out of steel or aluminum for the molds. And so that's pretty fascinating. I think the parallel that's super interesting to me on this is he talks about like OSH Park and the effect they had on the PCB services. So all of a sudden, instead of having to order like a huge minimum order with a high setup cost from a fab house, you could order, 3 boards for very inexpensive because OSH Park was ganging them up onto panels and then submitting the panels as if they were a commercial order. This is the same kind of thing. And so what they're doing is they're trying to figure out automated ways to take your CAD files and put them into a system that's going to be the most efficient possible at manufacturing that part. And then they just package them up and ship them out on the other side, all automated. The thing that you lose in that is if you go to a machine shop and ask someone to make something, they're going to tell you if it's not going to come out well because they know. And even, if it's a prototyping service, you used to have people that are looking at each order. I mean, the thought here is you're cutting those people out, and that's where the cost savings is. And so you send your file, an automated system puts it into production. A person doesn't see it again until it gets packaged, and they're not tasked at like knowing what you're trying to do or knowing what will work. Now, I got to say, Elliot, the thing about getting far away from the parts, that doesn't really bother me so much. You and I've talked about this several times. Like, both of us have in the past made our own circuit boards. I haven't made my own circuit boards in years. I'm to the point where I'm like, I will just order them. And they're so simple and inexpensive that they come, and almost always they work. I have that experience under my belt of making circuit boards. So I kind of know, what's going on and how to test them. Like footprints are a major problem. The tools have design rule checks, so you're more likely to not connect the wrong things together. There's just a lot of like safety, like guardrails along the way in doing these things. And I still have the cupric chloride in the basement, but I would really just like to get rid of it. And I'm wondering if we're going to see the same thing for like machined parts. That's it for this episode of the Hackaday podcast. As always, we'd love to hear from you. You can leave a comment on the show notes, which you'll find at hackaday.com/podcast. You can email us editor@hackaday.com. We live and die by the tips that you send us, so if you do something cool or you see something cool, we'd love to hear about it. tips@hackaday.com. And until next time,
keep on hacking.
Oh, what am I going to say about this one?
I wish I had that on tape. I wasn't recording when you said that.
The coup de grace is... The coup de grace? Maybe that's not right. Anyway, next hack.
Quick hacks?
Quick hacks!
Here we go.
I think that's it, Elliot.
I think that's it.
I think that's the last one. I've really enjoyed doing this with you.
I have super enjoyed doing them with you.